Hello. Now, students, we have been talking about the problems in dynamics of system of particles, and in our last class we solved few problems highlighting you the principles of Newton's generalized applications of Newton's generalized second law, then various equations of dynamics, for example the principle of equivalence, principle of impulse momentum, linear as well as angular. We have shown the applications of such group dynamics problems there. Now we will be taking up another problem highlighting another concept of the group dynamics. Let us straight away go into the problem. Now this is our example number 4 that we will be going to discuss today. So this is our example. I think it will be example 4. I think, let me just check the last example number that we have solved in our previous class, and that was, I think, example 3. Yes, so we will be going to now study the example 4 here. So let's say this is our example 4. And this problem is taken from the book of Merriam and Craig. The problem number is 4/26 as shown here. The problem states that the 3 small steel balls, each of mass 2.75 kg, are connected by the hinged links of negligible mass. So these are all the hinged links. So again we see that this is a rigid system. We have 2 rigid systems. This is one rigid system, this is another rigid system of equal length. So all these lengths are basically equal. The links are of equal length. They are released from the condition of rest in the position shown. So this is the initial configuration that has been shown here. We note that these are your initial configurations that has been shown over here, and they are released from the condition of rest in the position, and this slides down the quarter circular guide in the vertical plane. And when you see that if this is allowed to slide down because of the effect of the gravity, of course this is in the vertical plane, so that means here the G is acting in this sense. So this is the acceleration due to gravity that is there. It is shown that it is in the vertical plane. Now when the upper sphere, that means this is the uppermost sphere, reaches the bottom position, we have to calculate. You see that the spheres have a horizontal velocity of 1.56 meter per second. That means when this sphere comes to this position and we have the other spheres, we can draw the other spheres here like this. Say these are the other spheres position. So this is one sphere and this is the another sphere. It comes to this position, and at that position the velocity of each sphere, because they are all will be moving in translational motion, so at that point the common velocity of all these spheres is being equal to 1.56 meter per second. So that is the common velocity for all the spheres. Calculate the energy loss delta Q due to friction and the total impulse Ix on the system of the 3 spheres during this travel. Let us assume this direction. That means we say this is your x direction and we call the other as to be our y axis. So this is our axis. X and y axis are shown in this manner. So we have to calculate that if this is the initial condition, if the entire assembly is released from the condition of rest, and when it comes like this, that means the upper sphere comes to this position and naturally the other spheres will occupy this position like this, and having the common velocity, we need to calculate the total energy loss due to friction That means there is some friction here, and because of that there will be some energy loss, and we need to calculate the total impulse along the x direction on the system of the three spheres during this interval. I mean to say, from time t equal to 0 to this position, the time taken by this condition to come to this position. During this time interval, we need to calculate how much will be the total impulse being provided in the system along the x direction. We need to remember that this length and these lengths are all equal. That means at the initial condition, if you see the geometry here, if we like to draw the initial geometry here, we find that this is the initial geometry, and the two triangles are basically equal, and naturally these two angles will also be equal. That means this angle will become 45 degree, and this angle will also be equal to 45 degree. So we first mark this geometry here. Now, before we go to solve this problem, let us actually recapitulate one principle that we have discussed in our theory class. So going back to the theory class, if you recall that when we discussed the work done by the internal forces, so if you recall that this was actually the situation when we are dealing with the work done by the internal forces, and we noted that if we have the system of masses here, and when they are actually going by this work energy principle, we noted that the internal forces also contribute in the work function, and the total work done by the internal forces is actually, if we consider the two particle situation, this will be the total differential work done, and this total differential work done is the common internal force between these two into the difference in the displacements of the 2 points. That means if we go back to our case, just if we try to discuss the situation with our the rigid system comprising of 2 mass points interconnected by means of a light rod, we will see that suppose this is one sphere, this is the other sphere, and they are basically being connected. They are basically being connected by the light rigid rod. So they are being connected by this light rigid rod. So it is obvious that if we draw the free body diagram of the individual spheres, maybe if we see the free body diagram of this sphere and as well as this sphere, we will see that once I take this internal rod here like this is the cut portion of the internal of the rod in order to expose the internal forces. So we find that this is the internal force. We may call this as Mi, we may call this as Mi, and this we call it as Mj. So we can call this force as Fij, and we will be having the other force vector. This is the force vector here, and we may have the other force vector here, which will be something like this. And we know that this force vector is also equal to F bar Ji, which is negative of F bar Ij. That is known to us. So under such circumstances, because the work energy equation is individually applied for these two particles, now if we assume that the differential displacement this mass is having under certain occasion, let's say this is the differential displacement this mass is having. So let us say this is the differential displacement ds bar I, and let us suppose this is another differential displacement of this mass. We call this as ds bar j. So we note that the total work done by these internal forces here, we can say that the dWi, we can write the work done by the internal forces, say that is, we know, we have already seen that it is being given by F bar ij dot, it is ds bar I minus ds bar j. So that is how we can write our equation here. That is the total differential work done by these two internal forces. Here it is being given like this. Now also we know from our knowledge of system of a rigid system dynamics, we have seen that the relationship between the velocities, we note that the relationship between the velocities at the 2 points of a rigid system is actually being given by this particular equation. So if you recall that this equation is written as V bar I is equal to ds bar I dt. This is ds bar dt, and this we can say d theta dt. If we write it in this format, so V bar I is written as ds bar I dt, V bar j is written as ds bar j dt, and this angular velocity we write, this is the relative angular displacement, angle of displacement between the two particles, and we call this is has to be d theta dt. Then obviously we can see that this equation, we can say that ds bar I is equal to ds bar j plus, we can say this is d theta bar. So this is d theta bar cross, we have rho bar I relative to j. So this is what we can write it in the mirroring our equation of the velocity. So it is obvious that we say from here that it is obvious that it is ds bar I minus ds bar j. If we see here like this, it will be being given by d theta bar cross rho bar I relative to j. And for the plane motion, we know that actually if we see what will be the relative displacement, so we note that if this is the displacement ds bar I ds bar j, then we can say that this d theta bar cross rho bar I relative to j, this d theta bar is perpendicular to this, because you know this angle is going to be perpendicular, the angular velocity is going to be perpendicular to the relative position vector between these two. So it is quite natural that this, when I take the cross product, that direction of this cross product will be something like, we can show it here, since for the plane motion we note that this relative, the angle, because of that the relative displacement, this angular relative displacement that is going to happen will be obviously along this line, will be going to be obviously along this line, which will be perpendicular to this direction. That means either this will be directed this way or it will be directed in this way. But whatever be the sense, the direction of this vector is going to be like this. That means this is the direction of this vector. So that is going to be my differential relative displacement between these 2 points. So since we are going to take our work done, which is taken to be the dot product of the 2 vectors, that means this is one vector representing this differential displacement, relative displacement, and this is your force vector, and these two are going to be at 90 degrees with respect to each other. So obviously for a rigid system, when we are doing this, the result turns out to be as 0. It is because that this vector, which is actually, this vector is basically equal to this one. This vector is basically equal to this one, and we note that this particular vector is actually, this is the sense. So we can say this is the direction of, we can write this is the direction of d theta bar cross the relative position vector of I relative to j. So as a result, if we see that if we take the cross product, dot product of these two vectors, since these two vectors are 90°, so always we find that in for a rigid system, we find that the total work done by the internal forces is always going to be equal to 0. So that we can sidewise, verify it. This result was not obvious from our original discussion, but we can make a part of it and can make an adjustment here. That is, we can give a name also, that is the work done in rigid system. So it is the internal work done, internal force work function, we can say internal force work function in a rigid system. So this is the philosophy that we get. In this case, this result is going to be equal to 0. So for the consideration that we are having like this. So once this is being done from here, we can now focus and come into this problem. So it means that here we have two rigid systems again interconnected, and we can forget the work done by the internal forces which will be developed through the forces in these rigid links. So we can just forget them and consider the work done by all other external forces except these internal forces. So we here basically apply the work energy equation. Now why I am doing this? It is because here two configurations are provided and the information regarding the velocity is done. So therefore this particular problem basically highlights the principle of work energy equivalence. So this example will highlight the principle of work energy equivalence. So we will show you this problem as an application of the work energy equivalence principle in case of when it is being applied instead of a a single particle, when we are going to apply it for a group of particles. So we can come and use this equation. Now if you recall our work energy equation, the work energy equation tells us when we are having this group, we can write our work energy equation can be written in this format, that it is equal to summation I from 1 to n, the total work that is we are going to write, and the total work is of course is being given by, this is delta T, the change in kinetic energy, plus delta Vg, the change in gravitational potential energy, plus delta Ve, that is the change in elastic potential energy for each particle. We do this and find out this thing, that is the total change in the mechanical energy of the system is being equal to summation I from 1 to small n. We can write the total work done by the external forces. So we can say this is Fe bar I dot ds bar I. That means we can say that we calculate the work done by all the external forces other than that due to gravity and that due to spring, and we can include them and we can write, actually this is basically equal to the integration. Sorry, we should write this as integrated form. So it will be written in the integrated form. So this will be the integration. So let us write it in a decent manner. So we see that we write it in a decent manner. We say that it is actually equal to So we say this is basically equal to integration from S1 to S2. From S1 to S2, we can say that it is actually equal to, this is F bar E dot ds bar I, and this F bar E maybe that represents all the internal forces, all the external forces that are acting on the particle, and we can say this is the resultant work done. So that is the thing. But here if we look at this problem, we find that first of all these are all active forces, correct, other than that due to gravity and the spring. Now in this problem we don't have any spring associated here, so we can make this as to be equal to 0. So we can make this to be equal to 0 in our case, because here in this problem we don't have any springs. And also we note that the active forces here are in absence of friction, in presence of friction, the active forces of course will be the friction forces. So here there will be the work done. So on the right hand side of this work function, this will actually represent the total work done by the friction forces, because the normal reactions are not doing any work obviously, because they are perpendicular to the differential displacements. So here basically you will be having all these normal reactions like this. This is the normal reaction, this is the normal reaction, this will be another normal reaction, but all these normal reactions are not, they are actually the reactive forces, they are not contributing anything in the work equation. So ultimately we see that there will be some friction forces associated here, some friction forces associated here, as well as some friction forces associated here. So the friction forces basically will do some work. So we can say this represents the sum of the work done. So we can say this is sum of work done by the friction forces. And since the work done by the friction forces is considered to be the loss, the work done by the friction forces is considered to be loss, so I can rewrite this equation in the form, that it is T1 plus Vg1. That means 1 indicates the initial position. So this position which is being given here can be demarcated, can be categorized as initial configuration, and here the configuration that we are getting, we can configure it to be the final position. So I can rewrite our equation in this manner, that it is the initial total energy, and that must be equal to T2 plus Vg2 plus delta Q, that is the total loss or the total work done by the friction forces. So we can write it in this manner, that it is actually, because this is the friction forces, means that the work done will be basically negative. So since this entire thing is going to be negative, so ultimately I can write it, this equation, in this form. It is because if I replace this to be equal to minus delta Q, if I replace this by minus delta Q, the minus sign comes because it is the work done by the friction forces. Immediately one can find out this equation in this form, which represents the sum total of the potential energy and the kinetic energy in the initial condition should be equal to sum total of kinetic energy and the gravitational potential energy, along with the loss that is being produced because of the negative work done by the friction forces. So with this, if we come to the situation, now since initially we note that the system is released from the condition of rest, so it means initially the kinetic energy is 0. Now all the kinetic energy, actually this represents the sum, correct? We have this summation sign, so we need to put this summation sign over here, So we better write it in this manner. This is summation I from 1 to n, and here, here n is equal to, here n is equal to 3. That means totally we have 3 mass particles here. And here as well, we can write it in this manner, that it should be also the sum. This is equality, and everything is applicable for I. This is also for each I. I'm writing this is I equal to 1 to n. So in this case, we can therefore say in this manner that if we go on writing this for the 3 masses that we are having, we can say that individually all the kinetic energy at the initial condition is 0. Now we need to calculate the sum total of the gravitational potential energy in the initial condition. Suppose I consider this as this final position, this we consider as to be our datum. So we write this is as our datum. So you need to mention all these things. So datum means that here your Vg is going to be equal to 0, and anything in this upward direction is to be considered as plus, anything in the downward direction is considered to be minus. So since in the initial condition we note that everything is above the datum line, so we can calculate the respective heights from this datum line here. So it is pretty clear for the first mass, if we call this as the mass number 1, say this is M1, if I call this as M2, and if I call this as M3, right? So here for the first mass, we are writing this equation as, we can say this will be going to be M1 G H1 plus, we can say M2 G H2 plus M3 G H3, because in our case we note that n is equal to 3. We say here n is equal to 3. So that must be equal to, obviously, the sum of the total kinetic energy of the system. So I can say this is half M1 V1 square plus half M2 V2 square. First I write the general form of the equation, and then we will apply our simplification, plus half M3 V3 square. Then we have the gravitational potential energy. Now here, since this final configuration has been taken as the datum line, so obviously this part will be 0, and we have the loss in friction, that is delta Q. Now we note here, we see that here all the masses are equal. That means they are all equal. First, masses are all equal. So since the masses are all equal, I can simply write this equation in this manner, that since M1, M2, M3 are all equal, let's say they are equal to M. So we say that it is M into G into the sum total of these heights, that means H1 plus H2 plus H3. This must be equal to, we say from here, by taking M common, we say this is V1 square plus V2 square plus V3 square plus delta Q that we are getting. So plus delta Q that we are getting. Since our objective is to find out this energy loss, we can therefore further simplify this equation, can write that delta Q will be equal to M common, taking common, we can say this is G into H1 plus H2 plus H3. Then we can say this is minus half V1 square plus V2 square plus V3 square. Now we need more simplification here. First of all, we note here we just mention that since M1 is equal to M2 is equal to M3, M1 is equal to M2 is equal to M3, and we take them to be equal to N, let. Okay, so take them to be equal to N. Now again, looking at the mechanical aspect, since you see here the three masses are moving in a translational manner, so all the velocities of the masses will be basically therefore have to be equal. So since all these velocities basically are equal, so we can further write this equation as delta Q, that is the total energy loss because of the friction forces. It will be equal to m whole into, this is G into H1 plus H2 plus H3, and then it will be minus 3 by 2 into V square. So here we need to understand that the velocity 1, 2, 3 at the second position, at the position number 2, they are going to be all equal. Actually, we should have put the subscripts here for 2, 2, 2. This is written for position 2, but I am not going into that complex subscript, and I say that this is going to be my basic equation. Now out of that, again we note, since you see in the initial configuration the third ball is at the datum level, so obviously you see this H3 we can also take it to be equal to 0. So the H3 value can be taken to be equal to 0. Now we come and see, look at this figure and try to assess what will be the value of H1. So H1 is going to be this total height, which is nothing but the radius of this, the mean circular path, which is being given to be 360 millimeter. So we note from the geometry that the value of H1, so we just by the side, we just note that H1 is going to be equal to R, that is equal to 0.36 meter. That is the first thing. We note now H2. So how much will be going to be H2? So if we see here at this problem, so we note that from here we can say this H2, if we take this geometry, this actually represent, this height will be actually representing my H2. So this is going to be my H2, right? The height of the second sphere. So H2 can be written in this manner, that since this angle is theta equal to 45 degree, or we can take this angle also equal to 45 degree. So the cos part of it is this much. So we can say this is R whole into 1 minus cos 45 degree. So we can write this as to be equal to our H2. So we can say here that H2 is going to be equal to R whole into 1 minus cos 45 degree. So we can say that this is going to be equal to 0.36 into 1 minus cos 45 degree, so much of meters. So that is going to be my height for the second sphere. So if we note that if this is the height of the second sphere that we are getting, so now we can therefore implement this into our equation and can say that this will be delta Q, that is the energy loss, is going to be equal to m whole into G, and in place of this H1 we can put that this is R. So we can take this R common in fact from them, and can write that it is going to be equal to, this is R plus R, so it is 2 minus cos 45 degree. That means if we do simple algebra here, H1 plus H2, that will turn out to be as 2R into 1 minus cos 45 degree. So that is the thing that we are going to get from here. So we can say it is something like this, that it is GR into 2 whole into 2 minus cos 45 degree, and then we have this is minus 3 by 2, this will be V square. Now we are ready to substitute our numericals. So now coming to this, we say that this is delta Q, the mass of this body, or every mass are basically equal to 2.75 kg. So we can take this m to be equal to 2.75 kg. So we write this is 2.75. Then it will be, in place of this, it is going to be 9.81. The R value is known to be 0.36 meter. So that multiplied by 2 minus cos 45 degree. And then we have, this is minus 3 by 2, and the velocity square, that is the velocity, the common velocity was 1.56 meter per second. So we can put this value here. So now doing the calculation, we can write it in this manner. First we say 2 minus cos 45 degree. Sorry, we can say from here cos 45 degree minus plus 2 is going to be something like this, multiplied by 0.36 and then multiply it by 9.81. So that is going to be this much. Then we need to minus from here 1.5, that is this 3 by 2 into, we say that it will be 1.56 square. So 1.56 square. So the result turns out to be as 2. Then we need to multiply it by this factor called 2.75. This is the mass, the whole mass. So this multiplied by 2.75. So ultimately this is going to be, I think we made some mistake here in the calculation. Let me do it once again. This is going to be 45 degree cos, negate this value plus 2. So that is this total thing. Then multiply it by 9.81, then multiply it by 0.36. The result turns out to be this much, minus 1.5 into, this is going to be 1.56 into 1.56. The result, now it is to be multiplied by 2.75, and the result turns out to be as 2.518. So we can say that delta Q turns out to be as 2.518 joule. So that is going to be my first answer. That is the total energy loss that is taken place because of the effect of the friction. This is going to be this much. So we can write this as our answer. That is the first one. And there is a second part in the question which is asking us to find out the total impulse on the system of the three spheres during this interval. That means as the spheres pass through this initial configuration to this final configuration. So we need to calculate the net impulse to find out during this interval. Now the net impulse, as from the from the principle of impulse momentum equivalence, so we can say from impulse momentum principle, impulse momentum equivalence principle, momentum, in this case we say it is linear equivalence theory. We can say that delta Ix, that means, sorry, not delta Ix, that is the net impulse along the x direction should be equal to the net change in the linear momentum of the system along the x direction. So we can say it is delta of G sys along the x direction. So we can say that it is basically equal to G sys g cis x at configuration at time t equal to t2 minus it is g cis along x at configuration t equal to t1. So this is the net change in the linear momentum of the system. So we note from here that initially we don't have any linear momentum because everything was at condition of rest. But finally we see that all the masses are having the same velocities. So actually this is m1 v1 plus m2 v2 plus m3 v3 minus 0, and since all masses are equal and all velocities are equal, so basically they are equal to 3 mv. So since this is 3 times mv, so we can say 3 into 2.75, that is the mass of each sphere, and the velocity of all is 1.56. So we can say that it is going to be 3 into 2.75 into 1.56. So that is going to be 12.87. So we can say this is 12.87 kg into meter into second to the power minus 1, or you can say that to be equal to Newton second, or we can write this as 12.87 Newton second. They are all basically equal. So that is going to be my second answer for this problem. So let us now go and check this part from the answer provided in the book, remembering that this problem is, problem number, I think it is how much, 4 by 26. So we go to this in the answer section, finding out the problem 4 by 26. We see that delta Q is 2.52 joule. Let me just check how much we had calculated delta Q. So delta Q has been calculated as 2.518 joule. They are saying it is 2.52 joule, so we are correct. And then the Ix is 12.87 Newton second, and the Ix that we have calculated is exactly 12.87 Newton second. So students, therefore we can see we can also write it in this descent manner. Say we can actually reconcile our step and can write it like this. It implies that finally your Ix, that is the impulse provided to the system along the x direction, is basically equal to 12.87 Newton second, and that is going to be our final answer. So we can write it like this. So this is the way you need to produce it in your answer script during your exam. So students, you can therefore very easily see that this last problem that we intended to show you is highlighting the basic principle of the impulse and momentum, which was initially applicable for a particle, and then we extended it for a group of particles. Though in our work energy chapter we considered the some problems of the work energy in the group of particles, but there, here we made our foundation little bit strong by studying this sidewise feature, that for such a rigid system, the work done here, as shown here, the work done by all the internal forces is going to be 0, and we verify it from here, and thus we see that we can apply this basic principle to solve this problem over here. So students, I believe that with this help of the illustrated sums that we had carried out during our class will help you to understand the basic theories of the dynamics of the system of mass particles, and it will be helpful for you to solve the problems in the similar line. So when we meet in the next class, we will formally start the part 2 of our study, that is the dynamics of rigid bodies. Till then, it's bye from my end, and thank you for watching the video.